And we're going to try to go through Gaussian elimination and hopefully a little bit more today. So we want to talk about the mechanics for solving linear systems of equations. Okay, remember that's our goal. Before we get into it, there's a couple of people who are still not signed up on WebAssign. If that applies to you, let me just put this in the chat. If you're not signed up in WebAssigned yet, stay after class, and I want to figure out exactly what the problem is.
Professor Raymond, I just had a quick question about where you're posting the recorded lectures.
Yeah, so I'm trying to make a YouTube page to host these, but I'm having some technical problems right now. So they're not up yet, but they will be there eventually.
Okay, thank you.
Okay, so. Right, so that's that. So we started talking about Gaussian elimination last time. So I'm going to start sharing so we can so you can sort of follow the work with us. Screen. Oh, here we are. All right, so thinking about Gaussian elimination, really this is a method for sort of systematically solving linear systems. This works fine if you're working by hand, of course, when the system size is not too large. But the real sort of effectiveness of Gaussian elimination is that it lets you think about what you're doing when you're solving linear systems in a way that is fairly straightforward to program a computer to do. So that allows you to deal with very large linear systems, at least in principle, as long as your computer has got enough storage and working memory, you can effectively deal with an arbitrarily large system. Right, so the problem we're looking at is this, right? We have AX is equal to B. Remember, A with the double underline, that's a matrix. X is a column vector of unknowns. B is a column vector on the right-hand side. We call that the inhomogeneous term or the forcing or just the right-hand side. And the way we think about this equation is that we're trying to solve for the vector X. We want to get our hands on that vector, or another way of thinking about this is getting our hands on the components of that vector. So remember, if we write this out, the matrix A is a rectangular array of coefficients. If that matrix is M rows and columns, we've got M. Hello? Is there a question? Okay. If you have a question, please ask. Otherwise, please mute yourself so the background noise is not distracting. All right, so the matrix A has M times N coefficients, M rows and columns. There's going to be N unknowns, unknown components in our column vector X of unknowns. And there'll be M entries in that column vector B on the right-hand side. All right, so remember this is equivalent, again, another way of writing this if you write out all of the equations, right, you're going to have m equations. Okay, and what we're doing when we solve the linear equation really reduces to the things that we can do with these basic equations, right? So what are the operations that we are allowed to do? Well, it turns out that there's basically 3 operations available to us. We can multiply an equation by some non-zero constant. Okay, so if I've got an equation, I can multiply every term through in that equation by a number like 4 or pi or 17. And I don't change the information contained in that equation. Well, in terms of our linear system, ax is equal to b, right? Multiplying an equation through by some number has the effect essentially of multiplying every coefficient, all the a's and b's for that row of the equation through by the non-zero constant. The second thing you could do is you could add or subtract one row from another row. One equation from another equation. Okay, again. Okay, so please mute yourself if you are not asking a question. There's a lot of background noise. So if you take one equation here, you can subtract that from a different equation or add it to a different equation. If we go back and think of what's happening in terms of the matrix problem, essentially what you're doing is you're adding the coefficients of those 2 rows. And the last thing we could do is we could switch the order of equations. Okay, and rather than taking an arbitrary number of equations and scrambling the order, any permutation of the ordering you can always build out of swapping the order of 2 equations at a time. All right, so that's the easiest way to think about it. And again, that operation has the effect of switching the order of rows in the algebraic equation. So if you think about what you're doing with any of these operations, essentially all of these operate on the coefficients, the a sub ij's and the b sub j's. So you can organize, you can keep track of what you're doing. You can keep track of the solution process by just working with your coefficient matrix A and that vector B on the right-hand side. Okay, you don't have to explicitly write out the unknowns, the x1, x2, x3, and so forth. And the easiest way to do this typically is to build what's called the augmented matrix for the system. right? So we've got AX is equal to B. So we can build a matrix by taking our matrix A and appending to this the column corresponding to this B. So if we've got something like this system, so let me just give you an example. Okay, so this is a linear system we might want to solve. If we write this out in matrix form, we would get this problem. So this is our coefficient matrix A. This is our B. And this is our vector X. So the augmented matrix for the system is this matrix. Okay, and typically we'll put a line down here to separate the coefficient matrix from the right-hand side. Some authors don't bother with that, but either way, this is called the augmented matrix. So is everyone clear on what we're extracting from our linear system to build this augmented matrix? Is this clear to everyone? Okay, so I'm getting some yeses. So please ask me either in the chat or unmute yourself and ask verbally if there's any questions. So let's say we want to solve this system, right? So what were the steps that we talked about in Gaussian elimination last time? Well, we're trying to build our coefficient matrix so that it's going towards Rref form. Okay, and you could just as well look at this augmented matrix, right? And we want to work towards the Rref form. So the reduced row echelon form for that matrix. And once we've got it there, that will tell us everything we need to know about the solution. Okay, so let's think about doing that. So we look at our rows, we see there's no 0 rows, at least at the moment, so we don't have to move any 0 rows to the bottom. We're looking for pivots. So we actually have a leading 1 already in the first row, so we're good there. At this point, we want to make every entry in the column that goes along with our pivot 0. Every other entry, we want to get to 0, right? So that 4 underneath the 1, we want to operate to get that to 0. Okay, do you guys remember talking about this last time? Right, what was the Rref form? Right, all non-zero rows above any other row are 0. The first non-zero entry in a row, or the leading entry, first meaning looking left to right, has to be a 1. And then every other entry in a column with a leading 1 is a 0. So what we could do here is we could multiply row 1 by row 4, but by 4, and then subtract it from the second row. Okay, so 1, 2, 3, 4, 5, 6. Is there a question? Is there a question, anyone?
Yeah, so if we're multiplying the top row by 4, aren't we kind of removing the first criteria that we have?
Okay, so let me state this a different way. How about we say subtract 4 times row 1 from row 2, right? I'm not going to actually change row 1. I'm taking some linear multiple of row 1 and subtracting from row 2. So is that clear?
Yeah, that's better.
Okay. Sorry, that was unclear. So 4 times row 1, right? What are the entries there? That would be 4, 8, and then a 12, right? So multiply row 1 by 4, 1 goes to 4, 2 goes to 8, 3 goes to 12. And I'm going to subtract this resulting row, 4, 8, 12, from my second row. So 4 minus 4 goes to 0. 5 minus 8 goes to -3. 6 minus 12 goes to -6. Okay, so everyone follow that? Hopefully I didn't make any arithmetic mistakes. So what is our next thing we're going to go?
Professor,
Yes, go ahead.
could you quickly explain why we did that again?
All right, well, let's think about what we're doing in terms of the equation. Right, so that the augmented matrix we have is corresponding to these two systems, right? These two equations. Do you see that?
Yep.
Okay, so our criteria for the Rref form is that basically we want every unknown to show up in such a way that we can easily read off the solution of the system. Right, so I've got x1 here in my first row. I like that it's got a coefficient of 1 in front of it. I want to try, if possible, to get rid of x1 in every other equation. Right, that's the condition. I want to make zeros for every other entry in the column where I have a pivot, where I have a leading 1. So I like the fact that x1 appears here with a coefficient of 1. I want to knock x1 out of every other equation. And the way I'm going to do that is I'm going to take 4 times equation 1, and I'm going to subtract that from equation 2. Right, I'm going to replace equation 2 by equation 2 minus 4 times equation 1. And you can see 4 times equation 1 is going to be 4x1 plus 8x2 is equal to 12. Right, so the coefficients show up over here. When I subtract that the equations, I wind up with the following system. Equation 1 stays the same. Equation 2 is replaced by 0x1, or I don't even have to write the x1 there. 5x2 minus 8x2 is -3x2. 6 minus 12 is -6. Right, so you see the coefficients here and the coefficients here. So is it clear what we're doing?
Yeah, thank you.
Okay. All right, so we're going to continue trying to work towards the Rref form. I like the fact that I've got the 1 as my leading coefficient in first row. So let's look at the next row. Well, I've got a leading entry of -3. I want a leading entry of 1. So I'm not going to do anything to my first row. Right, I'm not going to do anything to the first equation. what could I do to the second row or the second equation? Well, I can multiply everything through by -1/3. And get to this, right? So now I have a leading entry of 1 in the second row. Okay, so everyone good so far? All right, well, pivot, every other entry in the column is a 0, good. So in my second column, I've got a pivot of 1 here, but I have this 2 above it. I want to get that to be a 0. So can anyone tell me, using the operations available to us, how could I turn that 2 into a 0?
You can subtract 2 times row 2 from row 1.
Exactly, very good. So I'm going to replace row 1 by 2 times row 2. So now row 2 stays just as it is. 1 minus 2 times 0 is still 1. 2 minus 2 times 1 is now 0. 3 times 2 times 2, so 3 minus 4 is -1. Okay, so now I'm all the way to RREF form. Or I should just say RREF. Leading ones, every other entry in the column with a 1 is a 0, and any 0 rows are pushed to the bottom. I don't have any 0 rows, so I don't have to worry about that. Now, why do I like this? Well, what's the equivalent set of equations? X1 is equal to -1, and X2 is equal to 2. Notice that once we get the system to RREF form, we can basically immediately read off the solution. Right, that's the whole point of getting to RREF form. And if we go back to our original set of equations, it's always a good idea to check your work. So let's try plugging this result we have into the original set of equations. X1 plus 2x2 would be -1 plus 4 is equal to 3, and that works. 4x1 plus 5x2, so that's -4 plus 10 is equal to 6, that works. So our solution, come on. We found by going through and pushing the augmented matrix to its RREF. Okay. So the whole point of doing this is that it gives you a path you can follow, which is essentially always going to work. Right? I've taught linear algebra or classes like 305 many times, and if you just have a set of linear equations and you're sort of trying to use your imagination to work towards a solution, sometimes it can get a little bit tricky. Sometimes students wind up going around in circles, but if you follow this procedure, start with the top row, find a pivot, make sure the pivot's 1, get rid of those entries in the column with the pivot, get all the rest of them to 0 if possible, and then go to your next pivot and keep doing that. This will always get you towards the solution. Okay. There may be some faster paths you could take if you see a trick, but this is always going to work, and this is something that you can always program a computer to do. Okay, it's always going to work. All right, well, let's say this was our linear system. So I just took the first equation from that previous set. I know that if I think about what this means, sort of in terms of analytic geometry, this is the equation for a line, right? So if x2 is 0, x1 would be 3. If x1 is 0, x2 would be 3/2. I could draw the line that goes between those, and I know there's infinitely many points on that line. Okay, I'm sorry, there's something going on in chat, which how did we get from -3 and 1 to -6? Michael, so let me try to make sure that this is clear to you. So how did we go from -3 and 1? So we're, Michael, can you speak to me here? Oh, you understand now. Okay. All right. Sorry, I missed that. So if I miss something that's going on in the chat, please just break in and let me know what's going on.
There it goes. I can watch it on here.
Okay. Sorry, I missed that. So there should be infinitely many solutions to this equation, right? I only have one equation in the two unknowns, x1 and x2. If I try to look at this in terms of the Rref form, right? There's only one row. This already is in Rref form. All right, I've got my leading entry is a 1, and there's basically nothing else that I can do. So what does that mean for us? Well, I'm not going to try to further manipulate this. And what Rref philosophy tells you to do is think about the infinite number of solutions here in a certain way. So so if there are infinitely many solutions, we can express them in terms of free variables, so-called. Okay, so what we do essentially is anything that's any variable that doesn't have a pivot associated to it becomes a free variable. So remember, what's a pivot? That means we have a leading coefficient of 1 in one of the rows of our augmented matrix. Right, so essentially what we do is we say x2 is equal to some arbitrary parameter t, and then we use the equation we have to write x1 in terms of x2 in this case, or in general, we express all of our variables in terms of the free variables. So x1 would just be 3 minus 2t. And essentially what you have here, you can think of what you're doing is you're parameterizing the solution. Note, this is a parameterization of our line. Okay, so think back to Calc 2 and Calc 3. If you need to parameterize a line, you could do that in terms of one unknown. If you had a linear system that was solvable and it turned out there were two free variables, you can think essentially of what you're doing as you're parameterizing a plane. In general, you can think of what you're doing as parameterizing your set of solutions as a sort of hyperplane, right? Right, so when we say free variable, what we mean is we can take on arbitrary values, right? So for any t I plug in, I can get an x1 and an x2 out. And remember the structure we talked about previously. So that this system can be solvable. We also say it's consistent. It could have one and only one solution. Or it could have infinitely many solutions. Right, if there's one and only one solution, that means there's no free variables. If there's infinitely many solutions, that means there's at least one free variable. There may be more. And the system could be inconsistent. There could be no solutions. Okay, so that's what's going on. And you can see exactly what's going on in terms of the Rref of the system always. All right, so let's do another example. Let's practice this a little bit.
Wait, so are we done with that example that you just gave with the like using t as a free variable? Like, was that it?
That's it for this one, right? This was chosen to be as simple as possible. But that's essentially all you can do if you have one equation and two unknowns. Is that okay?
Yeah, thank you.
Okay, so we really didn't have to do anything, and this was already given to us in reduced row echelon form. We just have to figure out how to interpret what does it mean to have a solution in this case, and you can do that by working in terms of the free variables.
Just
Okay.
a question for like when we do the WebAssign homework, does it matter like what variable we use, or like will it raid every like variable the same?
So in principle, so in terms of the linear algebra theory, you can always relabel your variables, so you can pick which ones you want to be free variables and which are the other ones. But I suggest not doing that. Take the system as it's given and use the criteria that we talked about, right?
Yeah.
If you have a pivot coefficient, then it's not a free variable. Otherwise, it is a free variable.
Mm.
So WebAssign is pretty good typically. It's pretty flexible, but sometimes it's not as smart as you would like. So I would say just try to work with the system as it's given to you.
Okay, thank you.
All right, so let's practice this. We've got x1 plus 2x2 is equal to 4 minus 2x1 plus 3x2 is equal to -1. All right, so augmented matrix for the system. We have 1, 2, 4, -2, 3, -1. All right. Can everyone see what we're doing to get from our system written out in terms of the equations and moving that towards the augmented matrix? Everyone good? Okay, so I see some yeses. I've got a pivot in my first row. I have a leading coefficient of 1. What could I do to the second row? How could I operate on the second row to get closer to Rref?
Add 2 times the first row.
Good, so I'm gonna do that. I get a 0. 2 times 2 is 4, I add it to 3, I get 7. 2 times 4 is 8, I add it to -1, I get 7. So what's our next step going to be?
Multiplied by 1/7.
Okay, I take my second row and I multiply by 1/7. Remember, I'm trying to get towards having a leading coefficient of 1. And what's my next step going to be?
Add 2 times the second row to the first row, or -2 times the second row to the first row.
Okay, sounds good. So 0 times -2 is 0 plus 1 is 1. 1 times -2 is -2. Add it to 2, I get my 0. 1 times -2 is -2. I add it to the 4, I get 2. And I'm now in Rref reduced row echelon form. And what is my solution? Well, x1 is equal to 2, x2 is equal to 1. And if we try plugging this back into our original system, it's clear that it in fact does work. So everyone following along okay?
Could you quickly repeat what you did to get to the last step?
Over here to pull out the solution, or the previous one?
The previous one.
This guy, okay.
Yeah, right there.
So I like my second row, right? Because I have a leading coefficient of 1 going left to right. And the first column is okay. I've got the 1, every other entry in that column is a 0. I want to get rid of this 2, or I want to turn that coefficient into a 0. So what we did was we replaced row 1 by row 1 minus 2 times row 2. Maybe I'll just do 2 times row 2.
That makes sense. Thank you.
Okay. All right, any other questions?
If we had a row of zeros, would that affect anything?
Well, the reduced row echelon form says you want to push the row of zeros all the way down to the bottom. For this particular problem, let's, okay, so does everyone have what they need from this page so far? Can I erase something? All right, so let's get rid of what we have here. And let's say that we were looking at a slightly different problem. Let's say we started from this problem. Okay, so we're going to have 1, 2, 4, minus 2, 3, -1, -1, 5, 3. All right, so let's go through our elementary row operations to get towards our Rref again. So I like that first row as it is. I'm going to multiply the first row by 2 and add it to the second row. And I'm going to multiply the first row by 1, right? So I'm just going to take the first row, add it to the third row to get my 0 there. Okay. So everyone following along so far?
Wait, can you say the steps again really quick? I was writing the matrix down.
So what we're doing, we're working towards our Rref form. So we have a leading 1 here. We have a pivot in the first row already. We want zeros below the pivot. So we're going to do something to rows 2 and 3. So for row 2, we replace row 2 by row 2 plus 2 times row 1. Right? That's exactly what we did before. And then for this row 3, we're just going to replace row 3 is going to be replaced by row 3 plus row 1. Right? So 1 plus -1 is 0, 2 plus 5 is 7, 4 plus 3 is 7. Okay, so now we have zeros below that pivot 1. Is that good?
Yeah, thank you.
Okay. So let's now look at the second row. Again, we can multiply through by 1/7. So we like that. And now we go to the third row, or we want zeros below that pivot. And above that pivot in the second row. So the first row, we could take row 2 times 2 and subtract it from row 1. Row 2, we're going to leave as it is. And row 3, we can replace by row 3 minus 7 times row 2. And notice that gives us a row of all zeros. If we write that back in terms of the original variables, notice what that's telling us. That row of all zeros corresponds to the equation 0 equals 0. All the coefficients in the equation are 0. So that's an equation which doesn't give us any additional information.
Can you repeat what you did to row 3 for the last
Now,
step?
row 2 and row 3. You see those two rows?
Mm-hmm.
So what am I trying to do here? I want zeros in all the entries of column 2, other than the one in row 2. So over here, what did I do? I replaced row 1 by row 1 minus 2 times row 2. And I'm going to replace row 3 by row 3 minus 7 times row 2. Right, notice if I multiply row 2 by 7, I'm back to 0, 7, 7. I subtract, I get all zeros. Is that clear?
Yeah, it's clear.
Okay. So this extra equation that I added is not giving me any additional information that's not contained in the first 2 equations. In fact, what did I do to quickly write this down? I just took the sum of the first and second equations and added that to my system. That's not giving me any additional constraints on x1 and x2. On the other hand, it's not it's not giving any additional constraints, so it's not making the system insolvable. The fact that this is giving me nothing extra shows up in the fact that that row of zeros is coming up. And the philosophy in the reduced row echelon form is any row of zeros just gets pushed down to the bottom. If it doesn't give you any information, just push it to the bottom. Okay, is that making sense? So someone asked the question of what does this row of zeros mean? So what it really means is that you had something in your original system that wasn't giving you any useful information, essentially. Are we good with that problem? Okay. All right, so some quick questions for you. Here's a system in terms of its augmented matrix. Can you tell me if this system is consistent or inconsistent? So does this, the corresponding linear system have a solution or does it not have a solution?
No solution.
All right, so I see inconsistent. So why is it inconsistent? What's telling you that it's inconsistent? Right, so I see 0 equals 5. Right, the third row here, this is 0 times x1 plus 0 times x2 plus 0 times x3. The left-hand side of the equation corresponding to row 3 is just a 0. The right-hand side is a 5. So that certainly is not a valid thing to say. All right, so before I go on, is that clear to everyone? All right, so another problem is this problem now consistent or not consistent? Consistent, I see. I have a row of zeros at the bottom, but that's doesn't stop my system from having a solution. So the next question, we know it's consistent. How many solutions are there? Infinite solutions. Very good. Okay, and if we say that the unknowns are x1, x2, x3, the way the system is written, I'm going to use x1 and x2 sort of as my standard variables. X3 is going to be my free variable. Right, I don't have a pivot for x3. So let's just get some practice extracting the solution. So x3 is equal to t. So the name you use for this label doesn't really matter. Right, t just means that x3 can take any value you want. How would you write x2? So look at the middle row here. x2 plus 2x3 is equal to 7. So x2 is going to be 7 minus 2x3, so minus 2t. Okay. And how would you write x1? How would you express the solution for x1? Think about the first row. What's the first row telling you? Okay, good. I saw it coming up in the chat. So that first row is telling you that we have x1 plus 0x2 plus 0x3 is equal to -4. So x1 is in fact fixed. x2 and x3 are going to depend on that on the t, on the that arbitrary parameter. All right, is this making sense? Please ask questions if you've got any.
Do you know that x3 is a free variable just because of that bottom, the third row?
It's not because of the third row, it's because of the second row.
Because there's a 2 for it in the second row?
Yeah, so, well, it's sort of, exactly what you pick as your free variables is sort of arbitrary.
Okay.
Okay. But you can follow the following procedure to get a way that's always going to work for picking your free variables. So we've got unknowns x1, x2, x3 here. And we have a pivot. We have a leading coefficient of 1 that in row 1 corresponding to x1 and row 2 corresponding to x2. We don't have a pivot for x3. So that's telling us, let's pick x3 to be our free variable. Okay. And if you do it that way, then that essentially gives you the way that makes it as easy as possible to read off a way of representing your solution from the Rref form of the system. Okay, that's not the only way to do it, but that's the way that makes your life the easiest, essentially.
Okay.
Okay.
So would a pivot for x3, would that look like a 1 in row 3, column 3?
Yeah,
Okay.
we would need a 1 there to have a pivot for x3. Okay, any more questions on this problem? So I'm glad you guys are asking questions. So let's do another one here. All right, so we've got a linear system. We put it into its reduced row echelon form. And let's say this is the result. So notice first row, we have a leading 1. Every other entry in that column is a 0, so good. Second row, we've got a leading 1 in the second entry. Every other entry in the column is 0. There's no other pivots. And we've got a zeros that's pushed all the way down to the bottom. So this is in its reduced row echelon form. Notice that there's 4 variables here, x1, x2, x3, x4, say. What would the free variables for this be? What's the sort of best choice to pick for the free variables?
Would it be x3 and x4?
Okay, that goes along with what we've been saying. So we could say x3 is S, x4 is T, or maybe T1 and T2 are the free variables. How would you express your solution for x1 and x2? So let's do x1 first. So that top row is telling you x1 plus 3x4 is equal to -1. So I just want to manipulate that to solve for x1. So x1 is -1 minus 3 times x4, so -3, and let's call it T2. Is this clear to everyone? Okay, so how about x2? This one's a little bit more work. How would you express your solution for x2?
Would it just be like x2 equals 3 minus 4t2 minus t1?
That sounds good. Yeah. Okay, and I just want to point out that we can express this in vector form as well. 1, 3, 0, 0. Okay. So now notice our solution, our system is consistent. We have solutions. In fact, there's infinitely many solutions. There's 2 free variables, so we have a doubly infinite family of solutions. We can write our family of solutions in terms of 2 arbitrary parameters, which you could name T1 and T2, for instance. And you can write out what's happening in terms of the individual scalar variables, or you could lump everything together and express your solution in vector form like that. So notice you sort of have a basic solution, -1, 3, 0, 0, and then you have an arbitrary multiple of this vector with entries 0, -1, 1, 0, plus a different arbitrary multiple of the second vector, -3, -4, 0, 1. Okay. So are there any questions on this one? Are we good? Okay, so I'm going to shift gears a little bit. Go back to vector algebra and matrix vector multiplication. Right, so linear combination of vectors. So all that means is that, let's say we've got two vectors, x and y, are vectors with the same number of components. Let's say n components. We're allowed to add or subtract the vectors, right? And you do that just by adding corresponding components. And you could take a scalar multiple of your vector by just multiplying every component. Okay, so adding or equivalently subtracting vectors and multiplying by a scalar are the linear operations. Oops. Okay, and in general, we say that we have a linear combination of vectors when we so if we have k vectors, x1, x2 up to xk, and k coefficients, a1, a2 up to ak, multiply vector x1 by a1, vector x2 by a2, and so forth, and add up all of those results, we say that we are taking the linear combination of the vectors x1, x2 up to xk. Okay.
Isn't that basically the dot product?
It's not the dot product because this k doesn't necessarily equal the number of components in your vector. So remember, the x sub i's are n vectors, so they have n coefficients. Okay, so here's an example. 1 times the vector 1, 2, 3, plus 2 times the vector 4, 5, 6. That's a linear combination of these two vectors with 1, 2, 3, this guy, and 4, 5, 6, this guy. That's not a dot product of two vectors. Number one, because the result you get is a vector. Right, so 1 times 1 plus 2 times 4, 1 times 2 is 2 times 5, 1 times 3 plus 2 times 6. So 1 plus 8 is 9, 2 plus 10 is 12, 3 plus 12 is 15. So linear combination of vectors just means you take some group of vectors, some collection of vectors, multiply each one by some scalar, and then add up all of those to get a result. Is that clear?
Yeah, thank you.
Okay. So I want to be absolutely clear here. This is not the dot product. It's just linear combination of vectors. Okay. So with this concept in hand, notice that we can think about the solution for our system that had free variables as a linear combination of different pieces, right? So I've got this basic piece, then some multiple of another piece plus another multiple of a different piece. So I've got a linear combination of three vectors, and in fact, an arbitrary combination because these coefficients are arbitrary. Okay, and how does matrix multiplication interact with linear combinations of vectors? Well, here's a linear combination of the vectors x and y. I take scalar a times x plus another scalar b times y. And essentially, I can distribute that multiplication and I can move these scalar multipliers out in front of everything. So notice matrix A times the linear combination of vectors is, in some sense, you could multiply A by each of those vectors and take the same linear combination of the results, right? These coefficients can get pulled to the front. So that's telling you effectively that the multiplication of a matrix and a vector is a linear operation. Okay. So we talked about matrix times vector multiplication and matrix multiplication previously. Let's see. Kind of running out of time here. Let's see, where do I want to? All right, so let's just do a couple of problems. So let's say we have this matrix A and this 2 vector B entries 5 and 6. Is AX equals B consistent? What do you think? So one way of attacking this is to look at the augmented matrix for the system. So is that going to be consistent? Are there solutions, or is it inconsistent? There's no solutions. Okay, so somebody says consistent. Do people agree with that? So how do we know it's consistent? Well, it's not good enough to say there's 2 variables, 2 unknowns, 2 equations. The 2 equations we have could be inconsistent. So what if we had the system x1 plus x2 is equal to 3 and x1 plus x2 is equal to 7? That would be a set of 2 equations and 2 unknowns that's inconsistent. So how could we check whether it's true, in fact, that the system is consistent, but we want to know this. We don't want to just guess this. Well, from what we've been saying, we know that we can, excellent. Somebody in the chat said convert to the Rref. So let's look at the Rref for this. Okay, so we can make that first entry a 1 just by dividing the first row through by 2 or multiplying by a half. Then we have -3, 1, and 6. And then we could make a 0 below that pivot entry of 1 in the first column. Multiply the first row by 3 and add it to get that 0. Multiply by 3 and add. So 15 halves plus 3 halves is 18 halves, would be 9. 15 halves plus 12 halves is 27 halves. And then you really don't need to do the last step here, but let's do it.
Can you repeat again how you got from the second step to the third step?
Over here?
Yeah.
So I know I want to make a 0 where I see a -3. So what I do is I take 3 times my first equation and add it to the second equation. So 3 times 1 is 3, add it to -3, I get 0. 3 times 5 halves, that's 15 halves. I add it to 1, or, oh, did I make a mistake there? Shoot. So 15 halves plus 2 halves would be 17 halves. So I made an arithmetic mistake there. And 15 halves times, sorry, 3 times 5 halves is 15 halves plus 6, that's 12 halves. So 15 plus 12 is 27 halves. And then once I see the 17 halves, I can multiply through by 2/17. So that would be 27 over 17, I guess. And I see here that I could go the next step to make a 0 here, and I'm going to have a solution. Certainly, this is going to be consistent. I don't have an inconsistent equation at the bottom in my Rref form, so I know the system has a solution. All right, so we're out of time for today. So thank you for your attention. If you're not signed up in WebAssign yet, please try to stay and chat with me a bit. Are there any last questions before I stop sharing the my work screen here? All right, so thanks for your attention, everyone. Have a good day. And like I said, please try to stay on if you're not in WebAssign yet.
Professor, I just had a question about the syllabus and or like a tentative schedule for the semester, when we're going to get that.
I'll try to get it up today. I'm sorry for the delay.
Okay, no worries. Have a good day.
Thanks.
Yeah, I also have a question about the syllabus. So I need a syllabus. Okay, so I remember last week, same time I consulted you about substitution of the classes. So me and my academic advisor and the associate dean of the College of Engineering are working on that. So I need a syllabus from you and about this course.
I will send it today for them. I just
yeah. Okay. So and I'm not set up for the WebAssign yet because I'm waiting for the results. Like, are they gonna agree or not? Because one of the professors says, okay, it's about to okay.
I couldn't understand the last thing you said.
It's like I did not sign the WebAssign yet because I'm waiting for the results for the decision.
Oh, okay.
So when the homework,
so you don't
when
have
the first
to,
homework,
you don't have to pay immediately. The first homework is due Thursday, so
this Thursday.
Yes. So it's your choice. You don't have to do anything if you don't want to.
Yeah, but the late penalty.
But so I can't tell you what chemical engineering is going to decide about whether this class can be replaced by something else or not.
Yeah, I understand. So they are evaluated. So the decision gonna made by the associate dean.
Yes.
Okay, thank you. May I ask him for an extension for the first homework? So
yeah,
I thought that
I can give you an extension if necessary. Don't worry.
yeah, because I thought the latest day they're gonna come out the results gonna be this weekend or this Friday. Because so once you set up the syllabus, I'm gonna send to my academic advisor immediately.
Okay.
I think that's it. Thank you.
Okay, thanks. All right, did you have a question for me? All right, I have to go. So if you have a question, please ask. All right, I need to go.